Today we're going to demonstrate to you some of the things we've been working on around robot hands, dexterity and telerobotics. We'll show you some live demos, we'll talk through some of the key features, some of the key parts of this, and then there's an opportunity to come up and book a slot for this afternoon where you can spend half an hour trying the system and actually get a feeling for getting a feeling with the Telerobot. We think that'll be really exciting for those of you who haven't tried anything with full haptic feedback and telerobotics. And also it's pretty cool if you've only tried controlling robots in the past. This is something else. So, let me get started. Who are we? Shadow Robot Company. We are, I think we're Britain's longest running robot company. We're just coming up to our 25th anniversary this afternoon. I actually have to dash off after this to get back to London to present our internal 25th anniversary celebration. These guys have already seen the slides, so they're not too worried about it, but for everyone else, the 48 of us, it's pretty exciting. Our kind of vision is to make awesome robots to make working lives better. We primarily sell these to people doing R&D at the state of the art in robotics, because it's still quite hard to get robots out of the lab and into the real world, as I think you all know. But what we're looking to do at the moment is to say, we can build and deliver dexterity. Where can that be applied? Where can that be used? And then what do we need to do next to make it more deployable? Maybe that's seal it so it can be put into an aseptic isolator. Maybe that's qualify it for higher levels of radiation. Maybe it's dust proof it. Maybe it's make it 10 times the size. We don't know, but we're open to all of those things because we are the people who designed and developed that robot, so we understand it completely. Great network of customers and partners we've worked with over the years. We do love development collaborations with people. We really enjoy getting very, very deep and dirty in the how on earth are we going to make this completely new thing work. So if you've got ideas for things that people who can do things like this seem like the right people for, come and talk to us. Flagship product is on the front here. It's the most dexterous robot hand available commercially in the world. There are a lot of things that say they're very, very dexterous. We think we're right up at the top of that game. We have 20 movements. In fact, 20 degrees of freedom and 24 movements. I get very annoyed with all these people who put up their under-actuated, two-actuator hand and say, it's got 20 degrees of freedom. And I'm like, no, it's got 2 degrees of freedom because you've only got 2 motors in. You can't claim those as degrees of freedom because you can't control them. How did you pass your kinematics exams? With this, we have the full 20 degrees of freedom. We have tendon force sensing. You'll see tendons going over the wrist around here. So 2 tendons for each joint, one to flex, one to extend. We have measure the force on those down in the motor current and temperature sensing, position sensing in each joint, and those big teal discs on the fingertips. These are SynTouch BioTac tactile sensors, which if I get the right one, yeah, you can feel that happening on the thimbles there. So this has got the full flexibility of movement of the human hand into pretty much the same size and scale. We cheated a little bit on the size. Can you hold it up like that, Seppi? So the finger measurements are all the same in length. They're taken off one of our engineers, and the thumb measurements are taken off another engineer. And basically they traded off who got to design the finger and who got to design the thumb, by which one, the one with the bigger thumb designed the finger. The one with the bigger finger designed the thumb. So they are human scale, just not the same human. And if you notice then, my little finger is considerably smaller than my index and second finger. On there we've used the same size finger for all of them, but we then have this extra flexion joint in the palm to allow the little finger to come up to oppose the thumb. So it's a really wide range of movement there. 2 degrees of freedom in the wrist, and then UR10, is it 10 or a 10E this one? 10E. 10E, a UR10E as the control platform. We use that because they're easy, they're safe, they're reliable, they're pretty robust, they're not stunningly expensive, and Universal know us well enough that they actually tell us how to do things with it that other robot manufacturers might go, we can't tell you about that. Somewhere we have the big spreadsheet of each firmware version and the way the network packets change, and it's a horrible spreadsheet. And the UR10E means you don't have to know about that anymore, but we spent some years being that embedded into the UR ecosystem. So we use that. This isn't a mobile system. Obviously, it's on a static base. There's a load of concrete blocks in the base there. But this is a nice 8 degrees of freedom to the palm, and then another 18 on into the hand. And you can see at the bottom there some of the things that OpenAI were able to do with this. I understand that the simulation, in the NVIDIA Isaac simulation, someone has actually replicated what OpenAI did in there recently, and graphic cards have moved on enough in the last 4 years that you can actually do that if you've got, is it an RTX 3080? Yeah, if you've got an RTX 3080 and you're not using it for Bitcoin mining. Yeah. Exactly, exactly. So we've actually seen this thing running in real life, doing the gating, and we're just like, what the, wow, yeah, that's really, really impressive. And that's a kind of an example of the kind of research partnership we do. So OpenAI came to us, they said, we want to use your hardware. We said, great. They said, we're breaking your hardware all the time. We said, great, how are you breaking it? They said, we're doing this. And we said, why on earth are you doing that? And that's a really stupid thing to do with a robot hand. And they said, because that's our learning system, learning how to do things. So we actually did a development program with them where over a period of, I think it's about 6 months, wasn't it? We increased the reliability 100-fold for the problems they were working on. So it went from they could break it in under a day to they could get a couple of weeks of work out of it before they broke it. They still managed to break it, they just had to try a lot harder to break it. And that kind of translates through into a practical improvement for real-world tasks. That's a really, really significant thing. When we find other ways people break it, we like to capture those, come back and say, right, how can we design that out of the next version? So I said we do a lot of R&D. We've done a stupid number of Innovate UK, Horizon 2020, and other European projects. We're winding down some of our European ones because they're less relevant to what we're doing at the moment. They're more around grasping control, and we're not very interested in the software control of grasping. We're very interested in the physical hardware and systems necessary to do dexterity. And that's still quite hard in terms of the software layer above that, but we think dexterity is where the real challenges are. So that's primarily the area that we're in. But we are very embedded in the kind of research infrastructure. I'm a director of EU Robotics, which is the Association of European organizations that do robotics research, and now a director of ADRA, which is the same thing but for AI data and robotics. And so we're involved in actually developing the European work programs and strategic visions and goals around how Europe will do AI data and robotics. The UK, I understand, has some plans as well in that area, but the Europeans have a bit more of an oomph behind it and a lot more people. So yeah, we do lots of R&D, we do a lot internally and externally, and we're always interested in challenges people haven't solved yet that could be done with this. Obviously, the big challenges that are interesting for people in this community are ones around protecting the human. How do you get it so that you can do that skilled, dexterous task with all of your abilities without restriction? How can you make the person safe to do that? How can you make it easy to do? How can you make it not physically demanding? How can you make it so that that guy doesn't have to retire at 50 because he can't stand being in a suit for 2 hours a day anymore? How can you make these jobs easier? And we think that this kind of hardware is the next step in that. We're not saying that we have a solution yet. We're fully aware that challenges of deployment, challenges of screening, contamination, getting the right levels of exposure for the system to be used in and so on, those are all there, but we are so much further ahead with this that we think it's the right point to start thinking about that step in the journey. How can we start to deploy this? This is never going to be up to the standard of a purpose-built hot cell master-slave manipulator, but I would say neither is that person. You'll put this in when you could put a person in, and this allows you to have that person standing at a safe distance, not wearing PPE, able to do the dexterous task exactly as they would have done if they were there, but with much more flexibility, safety, and comfort. So here you can see this is one of our standard proxy tasks. Joanna there is wearing, is she wearing the shadow gloves? Yeah, so she's wearing the other sort of gloves for this. I'll talk about the gloves in a minute. The difference is essentially to do with whether there's touch feedback, but you can see here she's just fairly fluidly operating the Telerobot, doing a simple dexterous task, sweeping some material up and putting it in a container. She has practiced doing this sort of thing, but she hasn't practiced a lot. She's probably had 10 or 20 hours of operating the Telerobot total at the point we did this video. And in fact, the bigger challenges here are usually getting your mindset around working with the much wider workspace of the robot. Can you just demonstrate the kind of clutching? Yeah. So the UR10 has quite a wide range of movement. The comfortable reach for a human is not the same. So to reach that, we have a foot pedal there and a clutching operation essentially on the wrist. So we can move the robot arm through a wide area, but then when we want to perform the task, we can do the task with the glove at a comfortable ergonomic position for the human. And it's the same way you use a mouse on a computer. You move the mouse across, bring it back, move it across, bring it back, just in 3 dimensions. Is it 3 or is it 6? No, yeah. So this is a non-tactile Telerobot system. Joanna has the advantage, though, that there is a certain amount of motion smoothing going on just because we're filtering the frequency of the response from the vives in case they get noisy. And that gives her a slight advantage. But still, Alex beats her playing Jenga, what, 2 times in 3 still? Or is it 50-50 now? Yeah. Yeah, Jenga as a service is not going to be our business model, but it could be an interesting added sideline. So we've got the motion tracking from the human to the robot arm, and then the tracking of the human fingers into the robot hands. We could put this on a mobile platform. We did something last year where we took a system over to Fraunhofer IPA and put it on one of their mobile bases and kind of ran it around in their lab for the afternoon, kind of going, yep, we can do that, we can do that, we can do that. The biggest challenge with mobile platforms is stability, because the problem is that if you've got a long reach arm that can move fairly quickly, getting the base to be stable means either it's going to be a huge base or you've done a lot of work on adding stability to it. So that's a kind of a challenge there. And obviously the other issue here is Joanna, Giuseppe are both standing in line of sight of the robot. They're both able to see it. If you've got a long distance between you, a mile, a million, 1,000 miles, how do you get that remote viewing? How do you get that ability to capture and see what's happening at the other end? So we're working with various techniques there. I mean, we've done it with as simple as a couple of Zoom calls and webcams, right? That does work at the basic level, but there's quite a lot of nice teleoperation remote viewing platforms and software around, ranging from things like Createx ISIS product to the work that Voices are doing and some other things that are kind of in the pipeline there. We know that's an active area of development. Other people are doing it. We're focusing on getting the dexterity part right. So the touch version of this, this is the one that you may have seen in the press more. So that's Mike from Haptic. He's the guy, they're the guys who make the gloves. He's wearing a blindfold, and you can see as he swipes the hand across, he hits the ball, and then he can feel that he's hit the ball, and he can reach and grasp it. And that's the glove. That's the earlier version of the glove that Giuseppe's got there. So when you come to test us later, you'll be able to try that haptic feedback. We've done that over long distances as well. We did that from the Wired office in San Francisco to our London offices with a mobile phone at the Wired end and a Zoom call. And the Zoom call had a video latency of around 3/4 of a second. And the 4G to our office had a latency on the tactile feedback of about 150 milliseconds. So we weren't crashing into things, which was nice. If it was the other way around, it could be more of a challenge. Touch sensors here are the SynTouch Biotax. I think they've been around in the literature for long enough that I can refer you to a 2011 paper by Fischl et al. And you can look that one at Fischl, Loeb et al. And you can look that one up. There are other sensor technologies that people are working on for this. The nice thing about this hand is it has a very modular fingertip. There's an M2 bolt there. You undo that. You can take the fingertip off and put a different one on. There's an SPI connector at the back of it. Provided you taught the right SPI protocol, your new sensor will just integrate straight into our hand. We aren't doing anything with touch sensing on the palm yet. The Haptic gloves will render touch sensing back to the palm. We're not exploiting that. And they also do resistance feedback. I don't know, do we do anything with resistance feedback? We're mapping the force data of that now, are we? Okay. So, yeah, so the tendon force data gets turned into grasping resistance feedback as well, which is quite nice. So yeah, we've sort of looked at the various problems that we are aware of where a telerobot could be applicable. This is marketing copy, apologies. But we're just trying to make sure that we understand where you think this could have an advantage and where you think we have missed something about that. Have we got it right? Is there a reason why you couldn't use this? Is there something we just don't know that we've not done? Or is it actually, yeah, we're starting to see that we could do this, but we'd never put it on a platform like that. We'd have to integrate. Those kind of questions, the how do we get from TRL5 to TRL7 questions are really the ones that we're interested in finding out now. We know we can build this, we know we can use it, what we don't know is can we use it to solve an actual customer problem in the real world. We've been looking at various ones in the last couple of years. This came because basically every time someone's data center goes down, we post one of these up on Facebook with a hug ops by our robot, kind of slightly cheeky, but we're trying to get the point across that a lot of the data center failures essentially come down to, it would have been really quick to fix that if we'd had someone in the building, but nobody lives near the data center in Iowa, so someone had to drive out there, and that takes 2 hours, and then they have to get in, and so it's like 3 hours before you can turn it off and on again. We can at least do the unplugging it, plugging it, turning it off and on again thing, and we can control it over a mobile phone, so you think there should be some opportunity there. You'll note that the Telerobot puts the USB plug in first time. there are some outtakes. Yeah. So it's been talked about in the press, it's talked about quite widely. NNL did a nice report for us a few years ago on enhancing glove box operations, where they considered this against the range of other systems that could be deployed for improving the way glove boxes worked. We think this is a step change in what you can theoretically do in teleoperation, and what we want to do now is to understand how we can turn this potential into a concrete action, how we can really get these being used by people. We like to joke that all the billionaires who've tried it have found it easy to use. That's great. One of the nice things about it is it's very, how can I put this, VIP friendly. We have another show reel with just a bunch of politicians popping up where it's like, yes, politicians use the system and clearly understood it without a science degree. Politician without a science degree has understood it and said, yes, I got this, I can do handshakes with it, I can shake hands. The key thing for politicians is shaking hands. And when they do a lab tour, this is always an easy crowd pleaser for them. But the thing there is, if you watch, he's just doing his natural movements at this point. He's not even thinking that he's controlling a robot. He's just performing for the crowd with a robot in front of him. And that's something you wouldn't do with almost any other kind of robotic system. So, our final slide, contact details, who we are, where we are. You can see us here. We're going to roll through some demos now. We're going to show you the hardware, talk through it, give you a bit more of a feeling for it. So I'll hand over to Alex for that bit. If you're interested in trying it, we're here all afternoon. Please come over and talk to Casper. And sign up for a slot this afternoon to have a hands-on go. We'll be doing 2 or 3 people at a time for that, because we have to walk you through do it like this. No, don't do that bit. And it's easier if there's only a couple of you, because then you're not breathing in each other's faces. And sign up for a slot and then come back. But in the meantime, Alex, over to you to run through the demo of the system.
All right, so we're going to run through some of the demos. The first one we're going to show you guys is going to be, it looks simple, but this is one of the tasks that we use to show the dexterity and how much force we can apply using the hand. So he's going to do some cup stacking.
The noise is the air compressor that powers the haptic feedback.
It started working? Okay. Okay. Are you going to stack the cups, not just put them back?
Yeah, I was stacking them so I can show that I can unstack them.
Oh, okay. But this cup, okay. So, as you can see, these cups, because of the ridge in the cups, they have a lot more pressure in them, so they're harder to peel off. Yeah, so obviously, because it's got one hand, we're not able to, when you normally have the biomanual system, you can use the other hand to help you with a lot of the other tasks. So what you'll see is that I will be using my hand to pretend to be the other system, but with Joanna in the video, she's able to sweep up, she's able to use the other hand to help her complete any of the tasks. Anything that has a weird grip, she's able to use that to help rectify any of the kind of movement issues that she might have with just having one hand. As you can see, because of the force feedback on the fingertips, he's able to feel how much pressure he needs to put on the cups, so the cups themselves aren't actually being indented at any point. It's fine. No, you're just going to do both of them. The feedback is also pretty instant, so lift your hand up. So if Beppe was to close his eyes, he should be able to feel the sensation of me pressing on his fingertips. So wiggle which one it is. Are you feeling it? Yeah? Yeah? Can you feel it? So as you can see, no, I didn't touch it. As you can see, it's pretty low latency feedback. So as soon as you touch it, he can pretty much feel the sensation in the glove. Yep. Do you want to pack these up for me? Are you going to knock them down? Go ahead. Casper can tidy up later. It's a better sweep motion than a flick motion. One of the things that me and Casper have been trying out in the office is with the biomanual system, trying to like the competition stack cups and seeing if we can get them up and down as quickly as we can.
What's your record for that?
It's still pretty slow. Nowhere near the actual like human doing the stack cupping, but it's a lot to do with trying to concentrate on using both hands at the same time. But once you get used to it, you're able to do it quite easily. Ready? So this demonstration is similar to a task that someone would be able to do. So, oh wait, sorry, 1 second. So as you can see, he's able to open the lid of this tin, empty out the content. It's always sod law that it gets caught on the edge. Sweep it around. So then he's able to move. We can change the brush. So we just use a paintbrush this time, but you can change it to like a swab or to any kind of like brushing, swabbing sort of material. As you can see, if we had the second hand, he would have been able to hold this himself. One more. Go down. Near that? Yep, that's it. The beauty of this as well is that the more you try to use it, at first when you try it, it's very intuitive. You can do a lot of tasks, but as you get better at it, so you learn little tricks that help you just get things done a little bit quicker. It's just like when you use your hand, there's like certain things you know what you can do with your hands to help you complete a task. You do this. Cool. So these are tasks that we've tried. But yeah, I guess like we have, if there's any questions you guys have, if there's anything that you would like to see us try before you guys can have a try yourself later. Or you can save it for when you come in later with your tasks, and then we can try and do those.
Sorry, Karen, you go first.
This is a silly question. I'm quite curious that we humans usually use these two fingers more for gripping and grasping. Personally, I don't use these two, but the hand has the equal capability of using all fingers. I don't know if there are some plans to trying to force or include in a way of the control to use all fingers, so you don't, for instance, wear down these two more. Because, for instance, I guess these two fingers are way more worn down now than these two, because we don't. That hand can do this,
yeah,
but we are not very good at using it.
Yeah, so even obviously because it's a human operating the system, I don't know if Rich might have an answer to this as well, but
I just made that. I think.
So yeah, definitely when I do a task, I definitely use those three more.
Yeah, it's not. I do it as well.
But definitely in certain situations, like for instance when I picked up the little kid, it was really useful to use those two fingers for a robotics. So like if I do that, and then I know I can use those guys to kind of do this kind of in-hand manipulation. So I think that tends to those two fingers. So that they also serve as supports and help also with the tactile feedback and understanding more where my hand is positioned. So especially in a unimanual situation, like it helps me flip stuff.
yeah.
Like the more you learn how to use it, then you can get like the art and use the fingers kind of.
It's potentially very useful.
Yeah, yeah. Because even with your own hand, you tend to use these two fingers to help with in-hand grasping and stuff like that, and giving extra support or playing a guitar. Yeah, so like of course like a human is operating it, so naturally the thought process is to use these two main things. But as you get better at it, you also realize you can do those in-hand manipulation tasks that you do as a human with the robot system, using those two fingers to help along the way.
I had only two fingers that I couldn't rotate that without the help of another angle of another robot. So I do this doctor in the full range.
Something we found talking to microbiologists, so we said biosafety level 3 and 4. Does everybody have all their fingers? And they stopped and they thought, and to be fair, the guy we asked this question was at the time the head of the European Biosafety Association. It was kind of his job to know. And he sat there for about 5 minutes and he said, losing a finger would be a career-ending move in our field. Because a lot of what they do is you take the lid of something and you then use your spare fingers to hold it so you don't put it down and cross-contaminate. So you actually turn your hand into 4 tools in a kind of weird Zoidberg style kind of way. And then switch back and forth between this hand and a 5-finger hand, and this is a 3-finger hand and a 2-finger gripper, which is kind of really interesting. We've not done a lot of that with this because it's obviously a concentration issue with trying to remember doing that while you're doing that. But it is something that people do learn to do when they're doing kind of some of these complex safety tasks where I can't put that down, so I have to keep hold of it, but I can now carry on and do something else with the other 3 fingers. I quite like the idea of swapping the fingers around and be like, oh yeah, that one's worn out, let's use 2, 3 and 4. So use these 3, and then eventually switch to these 3 or switch to these 3 or something. Being some challenges keeping the extra finger out of the way, but of course you have got, because it's a multi-finger hand with separate with driven fingers, if one is failing for some reason, you can almost certainly continue with the other ones and still get something done. To that point where you can improve that.
And with the hand as well, there's different sizes of the hand. So we do this hand, which is 5 fingers. Then we have the 3 fingers, 1 thumb, 2 fingers, 1 thumb. So then you can also kind of like allow yourself to take away some of the distracting parts of the...
Can you demonstrate that when he's not playing with a cup?
So we can do.
Yeah.
Yeah. Oh yeah. That one gets.
Is that one coming around?
So we have a set of parameters that you can kind of adjust
Yeah, okay.
in our mapping algorithm, and depending on the user, on the hand calibration and so on, and how much you prioritize orientation and position for each finger, you're able to do that. But at the moment, and in that, but to prioritize orientation for the little finger that will move.
Yeah.
More of that joint.
It's got the range of movement, but one of the issues here is that the haptics gloves have quite a big tactile thimble, and optimizing for being able to get contact means that you lose certain of your orientations.
Yeah, so one of the concerns here is putting sort of this sort of thing into difficult environments. But from your experience, what's on the hand itself, what are these sort of critical components? What are the components which are likely to fail?
depends what's difficult about your environment. So if your environment is dusty, then the fact that there are 4 big fans pulling air through the hand will probably be the biggest challenge. If your environment is wet,
they're pulling their
so
air through the hands because?
the airflow is in, through and down to keep the motor
Oh,
smooth.
that's magical.
Yeah, that could be done. We did a design study for ESA some years ago where we looked at using heat pipe cooling, but that would have to be done. Liquid could be an issue. This is not IP7, so that isn't liquid proof by design, but you could just put a rubber glove over it, a latex glove or something. That we've done that in the past and that does work. Hostile abrasion is a challenge because there's a tendon drive. If you abrade the tendons, they fail faster. Tendon material is a real problem, and there are still no very good robotic tendon materials, and we've been buying tendon for over 30 years and going, still not good yet. Talking to tendon manufacturers, and the problem is robotics is a very low volume market for it compared to almost anything else that it gets used for. So it's kind of hard to get better materials. So that's still a design challenge. If you've got radiation, then your electronics might become an issue. For the kind of design spaces where we're substituting for a human, I don't think that's much of an issue because that's going to be a fairly low dosage level anyway. Most consumer-grade electronics is okay for tens, hundreds of millisieverts without really a problem. We have tested some of our electronics, not these electronics, up to 2.5 kilograms for a whole assembly with 750 grays on the circuit board, and that was the point it failed. That's quite a high dose at some level, it's quite a low dose at another level, but in terms of deployability, we think that's kind of interesting. Obviously, we have the advantage that we can move some of the electronics further back. Tactile sensors you can't unless you build them in different methods. So if you really wanted a sense of touch on something that had to handle very hazardous high levels of emission, you'd probably be looking at something with a kind of pneumatic drive, remote sensing or something. I don't know, but I'm sure people have done some research on that. They just haven't looked at those papers.
But you've got wires all the way out to the tips.
Yeah, we have wire available there, and we could run air from the tip. The Haptics glove uses a valve feed to the fingertips, and actually the pneumatic bobbles there. So you can run air sensibly in very fine tubes over long distances. I haven't seen anybody do the reverse of that at this scale, but it could be done.
Any more questions?
When you put latex gloves to the hands, can you recalibrate the haptic sensor so that you don't feel the pressure of the gloves?
I would hope so. We've not tried it, but the latex glove is, depending on how tight the glove is, how much it's interfering with the hand, yeah, you need to pick the gloves right. If you talk to people who make gloves, they say, send us a form and we'll dip it and send you back a glove that's exactly the right size. So you could pass the latex glove that was built from a 3D print of the hand with that tactile sensor and then not have any interference issue.
Have you experimented much with having a haptic force feedback to the wrist or to the arm, rather than having free-floating VR gloves?
We haven't, but other people have. So Haptics have just, the people who did the force feedback, touch feedback, have just done a deal with Haption in France, and they've got some of the virtuose systems, and they're starting to do grounded feedback to a shoulder pack essentially. Don't know how well that works. It's not really been an issue for us because we've not been looking at kind of weight-based feedback, for which grounded feedback is particularly important. But I imagine if you're doing something where you, particularly we were talking to somebody yesterday who wanted to undo a nut that was torqued to 125 Newton meters, and we said, well, give me a 2 meter long spanner and I'll bang the end of it with the palm, and I might be okay. But yeah, okay, possibly won't do that. But if you're using the strength of the arm primarily rather than the dexterity of the hand, then yeah, grounded feedback is quite interesting.
You'd hold a nut runner or a bolting tool, not a... Yeah.
Yeah, if you've ever held a nut runner when it hits a hard nut, you'll know that you need strong wrists for that. That's another challenge. I mean, that said, you can also do some interesting things with cartoon physics to render your hardware back. So something we did try at one point was taking the estimated load on the wrist and using that to slow the arm down. So it's just like the arm's moving slowly, that's because I'm carrying a heavy thing. I move like that, but the arm's going like a tree. It's a possible way to do it, and I think, I talked about this before, there are lots of interesting ways you could render what's happening to the operator. The problem is, mostly they've been tested in isolation with a single point contact manipulator, rather than saying, hey, we can do dexterity, right, how can we communicate what's going on to somebody without interfering with their manipulation skills? I did once ask somebody from Sellafield who knew a lot about it, and I said, how often does a glove box operator kind of slip with something or maybe drop something? It never happens. Okay, well, one question, sorry.
So what's the payload of grasping and moving?
So the hand was designed with a nominal 5 kilo strength in some sense. We have footage of one of those hands holding itself on the bar, just hanging there, small to its own weight. The arm is a 10 kilo payload, the hand weighs about 4 kilos, so you've got probably as much as 5 kilos of strength available, but at some level we don't use all of that because essentially that's a wear factor. We could make it a bit stronger. I didn't see that, I wasn't watching. But yeah, so the design space for this was around dexterity and human-like movement performance, not strongman. There's plenty of big, strong hardware out there, right? If you want to punch a hole in the wall, KUKA have 13 different robots you can use to do that. However, if you want to actually get the manipulation part done, there's very little that can let you do that, so that's where we can kind of focus.
Yeah, I was thinking of handling different types of tools. That some of them are long and heavy, and they.
Yeah, we looked at that, and the kind of hanging tool thing that means it's essentially zero balance is quite nice for doing that. So you can basically then positioning the steering. There are some even nicer kind of balanced arm, kind of like high-end angle voice systems, basically to allow you to essentially position things that are heavy relatively neutrally. Those are all ways you can get around the problem. I don't suggest that this will do everything, but if you're talking about a 1 to 2 kilo hand tool with a reasonable amount of reaction force, you're fine. As soon as you start getting a big angle grinder and trying to cut through steel, this may not be absolutely ideal.
So yeah, if you want to speak to my colleague Casper, we can try and book you guys into some time slots today.